how might we think about this? So we have this alkyl bromide, and we're trying to make this thing over here, which is an amine, and we don't really have one step we can do this in, not even two steps, a little bit hard. We have to make a carbon-carbon bond, at least a carbon-carbon bond. How many people are trying to install that whole thing at once? And I think that's part of the problem. We just did a Grignard reaction a minute ago. That's an amine. So let's think backwards. Let's think retrosynthetically. Let's think about making this. And this is probably where you're finding it hard, okay? Probably most of you didn't think about this compound. Can we get from here to here? What do we have to do to get from here to here? We have to get rid of that oxygen, don't we? What do we call that? Is it an oxidation? Is it a reduction? Whenever we get rid of a carbonyl to a CH2 group, that's a reduction, okay? So we can actually do that reaction with lithium aluminum hydride. Okay. We talked about lithium aluminum hydride. We didn't really talk about this particular reaction. We talked about the fact that lithium aluminum hydride just throws hydrides on everything it can. It'll reduce carboxylic acids by pulling off the proton. It actually reduces the carboxylate. So you have an H- reacting with a carboxylate, a negatively charged thing. That's how strong a hydride donor, lithium aluminum hydride, is. So it can do that. Now, okay, we just made esters from acid chlorides. We can make down here, because I want room, because I need to do it. If we can make this, we can do the amide. Remember, acid chlorides will react with alcohols to make esters and with amines to make amides. They'll even react with carboxylic acids to make anhydrides. These things react with everything. They're very reactive. So they'll react with an amine to make that. We would probably, again, we would just throw an extra equivalent of amine in there because the other product we're going to make is this. So we would need to use two equivalents of our amine to get there, but we can do that. Buried in the notes, and this is the one reaction we talked about. That I said this is a hairy mechanism. We didn't do it. I might be able to give you up one step, and I expect you to do it, but it's actually not that bad a mechanism. We have this thing which is a tremendous electrophile. And we end up making the acid chlorides. That's how we make acid chlorides from carboxylic acids. That's one way. Another way is to use this compound. This is called oxalochloride. We could also use that to make a carboxylic acid chloride. Okay? So how did we make this? Well, we just magnesium. Make the followed by CO2, followed by H plus. Okay? So we take our bromide, we convert it to an acid. We take our acid, convert it to an acid chloride. Take our acid chloride, convert it to an amide, reduce our amide. Okay? Now, notice how I went about it. I went backwards. I said, how am I going to make that? Well, if I could make that, I could figure it out. And then that, I got back to here. Okay? And once I got to here, I was thinking from the other direction, but I continued to go backwards. So for doing multi-step synthesis, we want to try and think in both ways. The nice thing about this particular one is we do see our starting material in the product. We can see that. So when you think about things like alkyl halides, think about all the things you can do with alkyl halides. Okay? Think about your cheat sheets. Maybe in your cheat sheets, I put up on the board yesterday, it wasn't tremendously neat or anything, but we talked about all the things we can take alcohols and make alkyl bromides from them. We can make alkenes from them. We can make epoxides from alkenes. All of those things are interconvertible, and don't forget those things, those functional group transformations to get to where you want to be.